So we discussed how to determine the sign of delta G by looking at the enthalpy and entropy factors in the previous section. Now we want to actually calculate the value of delta and use that to determine whether a reaction is spontaneous or not. Again, keeping in mind that when delta G is negative, that's when reaction is spontaneous, and when it's positive, it is not, and when it's equal to zero, we're at equilibrium for that given reaction. So let's take a look at these three examples. Before we calculate them, I want to remind you that there are three different ways to calculate delta G. The first one is just using that delta G equal to delta H minus T delta S equation that we looked at in the previous section. The second one is very similar to how we calculate the change in enthalpy, delta H, which is using these enthalpy of formation values. Here we're going to use something called the Gibbs Free Energy of formation to help us calculate the value of delta G. And the formula is the same. You take the product's value minus the reactant value with each of the species multiplied by their stoichiometric coefficient. And then the last way to calculate delta G is Hess's law, which is the same concept we use to calculate delta H. Let's look at these examples now. The first one gives us a reaction here, and it tells us to calculate the delta G for this reaction. There's a couple of ways to calculate this delta G. You can either use your method 1 or you can use your method 2 here. There's no Hess's law method since we're not given several reactions to manipulate. So I've gone into our thermodynamic table to pick out exactly the numbers that we are going to need. So if you're going to use your delta H minus T delta S formula, then you're going to need to use these thermodynamic values to calculate the delta H and then the delta S, and then lastly apply it to that formula. If you're going to use your formation values, all you need is this blue column right here, and then just subtract the products minus the react, and you'll get your number. So I will do it both ways to show you that both methods give us the same conclusion in the end. So in method 1, all I'm going to do is using this approach. So that means I have to calculate my delta H, which I can do by taking products minus reactant of the formation enthalpy, and then I can calculate my delta S. In this case, I'm taking the molar entropy values from that thermodynamic table. So I get this for delta H and that number for delta S. I always want to remind people that the units are different for the two quantities, so when you bring them to calculate delta G, you want to make sure that you put them on the same unit. So here I put both of them in the kilojoules unit, so I keep the delta H the same, but then the delta S, I changed it to kilojoules with dividing it by 1,000, make it 0.9214 kilojoules per Kelvin. And when I multiply it by 298 Kelvin, I end up getting this value, negative 176 kilojoules, which tells me that my reaction is spontaneous because I have a negative delta G. Now, what about the second method? The second method uses that Gibbs free energy of formation, and in that case, I just plug in the number I have given in that thermodynamic table. I end up getting negative 225.78 kilojoules. Now, this is a negative number, so it tells me that the reaction is spontaneous. So in both ways, I found that my reaction is going to be spontaneous at 298 Kelvin. Immediate question that you might have is, why do we get different numbers here? So here we got negative 176, here we got negative 225. The reason primarily is because the delta HF, the molar entropy, and then delta G formation are all measured independently of each other, so there is some fluctuation in the measurements of these numbers. But the key point to take home here is that both calculations tell us that the reaction is going to be spontaneous at 298 Kelvin. Now let's take a look at the second example given in your lecture notes. And here we see that we're given a series of reactions. All of these are combustion reactions, and we were told to calculate the free energy for the reaction where methanol is produced from carbon monoxide and hydrogen gas. And so when you look at a question like this, the thing that should immediately jump up at you is the fact that we have few reactions. We can manipulate this reaction, so that means Hess's law, right? So we're going to work on that on the right side. What you want to do with Hess's law is always to take a look at all the reactions that you're given and see how you can get to the final reaction. The way I do this is I try to circle the species that I need at the end. So I need a CO gas in my reactant. So I look at all my three reactions. I notice that there's a CO right there, but it's 2. So that's something I need to work on. And then I need a 2H2 also on the reactant. I have a 2H2 on that second reaction and nowhere else. So that means that I need something to keep that. And then lastly, I need my methanol CH3OH in the product with the coefficient of 1. I have a CH3OH right now on the reactant, my reaction 3, so I need to do something with that. And so given the setups of what I want in my target reaction, I'm going to need to multiply reaction 1 by a half. That would make my 2 carbon monoxide become 1 carbon monoxide. I need to keep reaction 2 as is because I already have 2H2 there, so I don't need to change anything. And then I need to reverse reaction 3 because my methanol is given as a reactant, but I want it in the product side. And I also need to multiply it by a half because in the given reaction, my methanol has a coefficient of 2. In my target reaction, my methanol has a coefficient of 1. So those are the 3 things that I need to do to my 3 reactions. So these 3 equations here are the reactions after I've done all those 3 things to it. Now, you remember that if you were to multiply something by a half, that means you're going to multiply that delta G value by a half as well, which gives negative 257 kilojoules. I'm not writing the unit here just because of space constraint. Reaction 2 was unchanged, so the delta G is the same, which is negative 458 kilojoules. And then the last one, I reverse the reaction, which means now the delta G is the negative of whatever the original value is. The original value is negative 1378, so it's the negative of that number. And then since I multiply it by a half, I divide it by here as well, which gives me a total of positive 680 for that reaction. And then what I need to do now is add all the numbers that I have and then see if I get the total reaction that I want or not. So you notice that a few things cancel out. So the 2H2O are the same, and then one is on the reactant, one is on the product, so they cancel. I have 3 halves O2, 1.5 O2. I have a half, I have 1, so those cancel out as well. And then I have a CO2 gas on opposite sides, so they cancel out as well. So what I have in the end is CO, 2H2 on the reactant side, and methanol on the product side, which is this thing. And that's exactly what I want. So to get my delta G, I just need to add these 3 numbers, the negative 257, the negative 458, and then the positive 689. That gives me negative 26, which tells me that this is spontaneous. Let's now take a look at the last example on the calculation of delta G. So now we're given the reaction SO2 and O2 going to SO3, and we're asked a few questions about it. The first one is to just use the thermodynamic data to determine whether the reaction is spontaneous under standard condition at 25 degrees Celsius. And then in the second one, we were asked if that reaction is still going to be spontaneous at 900 Celsius. And here we're told to assume that delta H and delta S values stay constant with temperature. And then the last one is we're asked, what is the temperature at which the reaction goes from non-spontaneous to spontaneous? Okay, so we're going to have to calculate a value of temperature there. Let's start with part 1. All you need to do is just take a look at your thermodynamic values, which again, I've copied just the relevant parts here from that table. And remember that the last column here is the delta G formation value. So I'm just going to use that to make my calculation because that's the shortest way to get to my delta G value. So let me show you what that number is once I calculate it. And that ends up being negative 70.866 kilojoule, which tells me that the reaction is spontaneous at 298 Kelvin. But you will see that a lot of times this calculation that's done using the formation delta G is for 298 Kelvin because that's where those values were measured at 298 Kelvin. So just keep in mind that when you're trying to calculate at another temperature, you can't really use that number. If you're using that number, you're making the assumption that the value of delta G doesn't change with temperature, which is incorrect because we know it does, right? And in fact, that's what question B is asking. It's saying, at 900 Celsius, what is the value of delta G and is the reaction spontaneous or not? This is important because now you can't just look at the same number that you calculate and say, okay, well, it's negative 70.866, so it's going to be spontaneous, because that only applies to 298 Kelvin. If you're going to calculate it at 900 Celsius or 1173 Kelvin, you're going to have to use this equation, which is the delta G standard equals to delta H standard minus T delta S standard, right? So you're going to have to use that equation because that equation explicitly has a temperature factor here, which is going to give us a different delta G value. So for this, I'm going to have to go back to my thermodynamic table and find the delta H standard. I can use the formula of formation enthalpy, which is product minus reactant, to calculate it. And when I calculated it, I get negative 98.89 kilojoules. For the delta S standard, I can use my molar entropy values again from that thermodynamic table, and I found that the number is negative 196.598 joules per Kelvin. Okay, so remember that that's the unit of entropy. And now I'm going to put it together to calculate delta G at 900 Celsius or 1173 Kelvin. So keeping in mind that when I do these calculations, I have to use Kelvin because it has to do with the use of the gas constant later on in order to do some conversion. So having that as my delta H and then my delta S, remember that I always want to make sure the units are the same. So I convert this to kilojoules, which means dividing by 1,000. So now I have negative 0.196598 kilojoules per Kelvin. So when I apply it in that formula, this is what I get in the end. I get a value of delta G standard equal to positive 131.719 kilojoules, which tells me the reaction is no longer spontaneous at 900 Celsius or 1173 Kelvin. So earlier it was spontaneous at 298 Kelvin. Now at 1173 Kelvin, it's no longer spontaneous. So this is one of those reactions that is spontaneous at lower temperature, but not spontaneous at higher temperature. The third question asks, well, when is that conversion happened? When from spontaneous to non-spontaneous, right? When does this change occur? Okay, well, we can calculate it because we know that the conversion is going to happen when delta G goes from a negative number to a positive number. Well, going from negative to positive requires you to cross through zero. So in other words, we can find that specific conversion temperature if we set our delta G standard equal to zero. And that's what I'm going to do here. I'm going to say delta G is equal to delta H minus T delta S, but the conversion will happen when that delta G value equals zero. So then that allows you to rearrange the equation and write it this way, delta H equals to T delta S, and then solve for T, which is just equal to delta H standard divided by delta S standard. My delta H is negative 98.89 kilojoules. My delta S was also a negative number, and again, I'm expressing this now as kilojoule, keeping in mind that the unit is kilojoules per Kelvin here. And dividing those two numbers by each other, the kilojoules will cancel away. I just have Kelvin in the end. And that should give me 500 Kelvin. So basically around 500 Kelvin, that's when the temperature conversion is such that above that temperature, the reaction is no longer spontaneous, and below that temperature, the reaction is spontaneous.